Hi guys, welcome to our channel of Sciences and Mathematics. Today we're going to learn a concept in chemical kinetics, and we're going to use the sample question on the board to try and answer some of the questions and try to see how we can be able to describe different orders of reaction rates in different maybe aspects of chemical kinetics. But in our case for today, we're going to look at a zero order rate, a zero order reaction rate, and we'll try to see on how we can be able to solve the questions in A, B, and C that is listed on the board. So for that case, thank you and welcome. So as I've said, today we're going to look at a concept in chemical kinetics, and that is going to be in the form of a sample question, but as usual, we'll try to look at some of the concepts that we need to solve the problem, and then we'll proceed and try and see how we can be able to tackle the problem that is listed on the board. So in this case, this problem comes from the concept of chemical kinetics. And as we said, we're going to have a short recap, of course, to assist us understand how we're going to solve that kind of a problem. So the problem states that a zero order reaction has a rate constant of 0.015 moles, that is moles per liter per second, at a certain temperature. If the initial concentration of the single reactant is 1 mole per liter, that is 1 molar, A, find the concentration after reaction time of 5 seconds at this temperature. B, find the time required for all the reactants to react at this temperature. And then C, final, find the value of the half-life of the reaction. So in this case, we're going to look at what a zero order reaction is. And we said from the concept of chemical kinetics is that the term chemical kinetics or kinetics assists us to answer the question on how fast a reaction proceeds. And this basically is due to the fact that we cannot be able to measure or the convenient way in which we can be able to describe the speed of a reaction is using the concept of rate. And rate, basically, we said it is the rate of the change in concentration of a reactant over the change in time for the period for which the reactant has changed. Now, this is a form of equation that we had used, of course, to describe the speed at which reactants can disappear or the speed at which the products are formed. Of course, we had a general equation for description of how maybe we can describe a reaction that involves the reactants A and B, which is forming products C and D, whereby these coefficients that we use here are used, of course, to describe. From the stoichiometric equations, we know that the coefficients are used to describe the volumes, the reactant way in which we are going to describe this reactant being represented as 1 over A change in the concentration of A over change in time will be equal to negative B change in the concentration of B over change in time, which will be equal to positive C. This is a change in the concentration of C over change in time, which will be equal still from this 1 over D change in the concentration of D over change in time. Now this basically, if you can see that from our reaction, the general reaction we had, A and B were forming what we call the reactant, and C and D were forming the product. So in this case, we have designated negative values for the reactant, where we have put a positive value for the product, which implies basically when a chemical reaction is taking place, there is a decrease in the concentration of reactants, while there is an increase in the concentration of the product that is being formed. Now, from this concept, we had what we call a reaction order. which we use to describe different ways in which this rate of chemical reactions or the reaction speed of reactions can be able to be described. So basically the reaction order implies the power dependence of rate on the concentration of the reactants. And we're going to see that we have different orders of reactions ranging from zeroth order, first order, second, and we can have even the nth order for that case. And then we have already looked at some of the concepts in our videos describing the following order of reaction that we have talked about. So as we say, I'm just assuming that maybe we have just been conversant with those specific symbols, that this is a concentration of A, either being a reactant or a product. And this concentration is given in form of moles per liter, which is given as capital M molar. So in that case, of course, we are going to see that the rate now, the rate can be described, or the units for the rate, as it is change in concentration by change in time. This is molar per second. So in this case, these are the units that we're going to designate for concentration. So we also had a way in which we had represented some of the, in our introduction video to chemical kinetics, we had a way in which we had represented the first or the zeroth order reaction, and we said that for a zeroth order reaction, like in the case of the one that we have been given, for a zeroth order reaction, this refers to a reaction whose rate is independent of the concentration of the reactants. So therefore this one implies that the change in concentration, we use these symbols for the sake of a summary. So this implies that the change in concentration of reactants or a reactant is or produces no effect. So this applies therefore for a zero order reaction, whereby the change in concentration of the reactant produces no effect to those. So therefore that is where we concluded that a zero order reaction is a reaction whose rate is independent of the concentration of reactants. Now we're going to have a specific expression or equation that is going to represent the zero order reaction, whereby the rate is given as R, which is equivalent to K, whereby K is a reaction constant and R represents the rate. So therefore, as we said, the rate is a change in concentration over time. We're going to give this one as, this is a development from the instantaneous rate that we had given as this was a change in concentration, a change in time, which reduces to the limit which is given, of course, d changing A over dt. So this form of an equation is going to give us a constant from the relationship of this equation, the first equation that we had given for rate. So therefore, we're going to describe this equation in the form of an integral, which is going to describe for us, of course, the nature of this rate of reaction, which is a zero order reaction. So therefore, in the integral form, this equation is going to translate into, this is the concentration at the time t is equals to negative kt. We said the implication of that negative sign is a decrease in concentration plus the initial concentration of that specific reactant. So in this case, this is the general equation that we are going to use in solving our equation that we have given on the board. And we're going to see that this equation is analogous to the equation of a straight line, which of course states that y is equals mx plus c. where the C constant represents that's the y-intercept represent the initial concentration of the reactants. T is time, and then K is going to be the slope of that specific line or graph, which is going to represent the negative form of which is going to represent the form of our reaction constant, which is negative. Okay, so therefore we're going to have a slope with a negative gradient from this equation. So I just state it somewhere, and then we just go to, I'll just proceed to just tackle our question. So therefore, before we do that, there's a specific concept which has been mentioned in this particular question, especially for the choices of, for the questions of A and B, where it says find the concentration after the time of 5 seconds at this temperature. This a concept of temperature which has been mentioned inside there, and I feel that it's necessary for us in order to just have a mention of some of the factors which we have mentioned which affect the rate of reactions. Now that temperature has been mentioned, we can just have a quick summary of some of the factors which affect the rate of reaction. And one of them, of course, from the one that is mentioned, is temperature. And then the second one, we're going to have a action of catalyst, or just a catalyst. This one reduces activation energy, so therefore it's going to have an effect on that. And then we're going to have a surface area, it's a surface of reactants. And then lastly, we're going to have pressure, and this applies to gaseous reactants or products. So therefore, apart from the temperature which is mentioned here, these are some of the factors which are going to affect the rate of chemical reactions, or the rate of reaction rates. The first one is temperature, action of a catalyst, surface area, and then pressure, and that one applies to the case of gaseous reactants or products. So therefore, we will just go ahead and try to solve our question. So we start with that is A. First, by extracting the information that we have been given from the question, a zero order reaction rate. So we have mentioned that in finding the parameters of a zero order reaction rate, we are given that the concentration at the time t is equals negative kT plus a concentration which is an initial concentration. Therefore, we're going to use that. So this is for a zero order. A zero order reaction as a rate constant. So K has been given as 0.015 moles per liter per second at a certain temperature. If the initial concentration of the single reactant is 1 mole per liter, so therefore this is our concentration is 1 mole per liter. Just mention it there. Find the concentration after the reaction time of 5 seconds at this temperature. So the T is equals 5 seconds. Find the concentration after. So we've been requested to find the concentration at T, which of course we have said is equivalent to, we do a substitution for this negative reaction constant 0.15 times T 5 seconds plus the concentration initial is given as 1, so we are going to have 1. I've just deliberately eliminated the units for the sake of space, because we're just going to integrate the units for concentration. So this is going to give us a figure. After 5 seconds, we're going to get a figure of 0.925 molar. That's going to be a concentration after a reaction time of 5 seconds at that specific temperature. So we're going for choice number B. Find the time required for all the reactants to react at this temperature. So from this we can be able to make time the subject of that formula by finding that T is equals, so this one we are going to have the concentration at T minus the concentration initial divided by negative K. So that is going to give us the time required for all the reactants to react at this temperature. So we just do a substitution whereby we have negative K. So K for us was that one. So it is 0. Okay, this is the concentration at this specific point. So K for us is 0.15. And then we have the initial concentration, of course, which has been given as 1 mole, which is this one. So we do a substitution for that, 1, 0. And then we have at T equals 5, the concentration will be 0.925. So we will do a substitution for that here, 0.925. So therefore this is going to be negative 0.075 divided by negative 0.015, which is going to give us 5 seconds. So that is for choice B, for the question B. And then the last one, find the value of the half-life of the reaction. So half-life for a zero order reaction is given using the equation. So that is for C. Half-life is given using the equation T half is equals initial concentration over 2K. So having done those specific calculations, we know the initial concentration was this one, 1 mole, 1 molar, and then it is 2 times the concentration, this rate constant, 0.015, which is going to give us 3 seconds. So that is for T half. And half-life in this case represents the time taken for the half of the reactants to be consumed, and that one basically represents half-life. So I hope that we have understood how we can be able to do a zero order reaction rates using the formula that we've listed on the board, and we're going to have more examples that we are going to tackle using the same in the concept of the chemical kinetics. So in this case, if we have maybe a query for us, you can just do it in the comment section so that we can be able to handle it and share information and try to improve together. So for that case, that is it for today. Bye guys. Thanks.